All right, here we go. 2.1, 5.3, 15.1. So we're starting on page 21 here. They're talking about the Tohoku earthquake. Basically generated a big tsunami that hurt one of the nuclear power plants. So that's what this story is talking about here. So we're starting on page 22. Zoom in a little bit so we can see what's going on in that one. Page 22. So conservation of matter. So what is here has always been here. And the big thing about that, like there's a big law of kind of conservation of matter. You know, it's going to be whatever's here is just going to get simply recycled again and again and again and again and again. You must know the most abundant elements, okay? Oxygen, hydrogen, silicon or silicone, excuse me, nitrogen, and carbon. Okay, you got to know those five. All right. So a lot of this here is talking about, you know, like matter and atom structure and things like that. You don't necessarily need to know the structure. It's not going to be asked about directly, but just having the basis of, you know, there's the neutron and the nucleus, there's neutrons and protons, the electrons go on the outside, kind of that basic understanding. You got to know how that works because a lot of like ozone concentration deals with electrons leaving with oxygen and chlorine, and we'll get to that a little bit later on. All right, so flipping page, now we're at 24. Okay, this is talking about the nuclear legacy in the Pacific Ocean. It's kind of an interesting read on basically kind of like what's going to be happening here. So go to this graph here. You can see ocean concentrations of radioactive cesium-137 show evidence of nuclear accidents at Chernobyl and Fukushima. So you can see basically big gigantic spikes. Starts to drop big gigantic spikes. So you can see basically the nuclear energy stuff, when there's accidents, it hits the ocean as well. All right, so page 24. Okay, so radioactive. Okay, definition. It focuses a great deal of energy in a very, very, very small area. Okay, that's one of the reasons nuclear power plants have such big kind of containment areas, because there's so much energy concentrated in such a small area. Okay, a half-life. Hopefully you guys remember this term from chemistry, okay? This is one of the things you're going to need to know. So half-life, the amount of time it takes for one half the atoms to give off radiation and die. And the half-life for different things is different time frames. Like we use carbon-14 dating for things that are kind of like more recently passed, because that carbon-14 has a half-life of about 14,000 years. Uranium, though, from uranium-235 from nuclear power plants has a half-life of a couple million years. So it's going to take a long time for all that stuff to go away. All right, flipping to 27. Dealing with pH here now. Okay, so if it's an acid, that means that the hydrogen ions, the number of hydrogen ions is greater than the hydroxide ions. Okay, you got to know the difference between these. So acids, more hydrogen ions. The base, the hydrogen ions are less than the hydroxide ions. Our pH scale goes from 0 to 14. That's acid over there. There's bases over there. Pure water is 7. Okay, you can see your stomach acid 1.3 or 1.5 to 3.5. So basically the acid for stomach acid would be down here. Okay, most household cleaners are actually bases, because as bases come into contact with dirt, they naturally create a soap. And that's why when like you spray Windex on the window and you're cleaning it, your hands kind of feel slick. That's because your hands have oil and dirt on them. Naturally creates a suds. All right, also on page 27, talking about organic compounds have carbon atoms. Inorganic compounds do not. Pretty straightforward with that. So I love the section in the grocery store where like, oh, come and eat organic. Well, everything in the grocery store has carbon atoms. That's the whole point of, you know, food has carbon atoms, and that's what we need to eat to make stuff, to make it healthier for our bodies. Okay, the building blocks of life, you can see there: proteins, nucleic acids, carbohydrates, lipids. Basically, think of it as like meat products. Nucleic acids is basically everything that was alive. Carbohydrates like breads and pastas. Lipids are fats, so like oils, like avocado is a good lipid source, things like that. All right, so this here, you can see energy and introduction. This would be section 2.2. So we're going to skip from there. Got my little tab ready. We're going to jump over to 5.3, biogeochemical cycles. So now I'm on page, you can see there, page 117. So I'll take that out of the way now. Okay, so the vocab you need to know from this term. Okay, a reservoir, residence time, flux, source, and sink. All right, and most of them you can see are literally right there. Okay, nutrients and other materials move from one reservoir or pool to another. So for example, Okay, like the fossil fuels that we have, that's a carbon sink or carbon reservoir. Okay, let's just say that that's down, there's the Earth's crust for whatever reason. I know I'm an awesome drawer. Okay, but if we pull the fossil fuels up to use them as fossil fuels, I'll draw a sweet little car here. Go there, and then the trunk, and then there's the top, and there's the, yep, sweet. I gotta put a door on here. Man, I should really that award for how great my drawing is. All right, so the fossil fuels go into the car. Okay, that's the exhaust, by the way. Okay, fossil fuel. Now that carbon is now up in the atmosphere. So we have gone from the reservoir of the Earth's crust or the geosphere. Now we've gone up to the atmosphere. Okay, that's moving from one reservoir to another. Okay, the residence time, you can see it there, residence time, that's how long it's going to stay somewhere. So the carbon and fossil fuels, that was there for millions of years. All right. The flux is basically, you can see the definition right here. Am I still on screen? The rate at which materials move between reservoirs is termed a flux. So right now, the flux that we have going from the geosphere to the atmosphere of fossil fuels is really high. Okay, we're moving a lot of stuff from the geosphere to the atmosphere. And that's a problem because, again, it's the speed of change that makes a problem in the world. Okay, the source and sink. Okay, when a reservoir releases more materials than it accepts, it's called a source. So in this case, the geosphere would be the source because it's releasing more than it's accepting. Okay, when a reservoir accepts more materials than it releases, it's called a sink. So the atmosphere, that would be your sink in this example. The geosphere would be the source. All right, this diagram on the bottom shows it really good as well. Okay, so if there's a small movement or not as much is moving from here to here, it's a small flux versus a large flux. So in our example, going from fossil fuels, geosphere into the atmosphere, that's a large flux going on right there. All right, flipping to page 117, or excuse me, now 118, I simply say you should know this, okay? Because I'm pointing to, I should probably put like a little arrow here. Okay, you're basically talking about this figure here, figure 516. That's the water cycle. All right, this of all the cycles are pretty straightforward. I'm confident you guys have heard of this one, you guys have practiced with this one, and so on. Okay, so you got precipitation and runoff and evaporation and so on. Like, I'm confident you guys know this, so I'm not going to go over too much detail about this. Okay, page 119. Say, you should know this. Okay, good examples of human impact. Our impacts on the water cycle are extensive. One of the things you need to know for the APES exam is examples of how humans have impacted things. Okay, so good examples, that paragraph right there is a really good kind of example of what's going on. So that's page 119. All right, also on page 119, I put carbon reservoir, sedimentary rock, and oceans. Okay, a big thing for the oceans right now that's really good for us is the oceans soak up a ton of carbon dioxide. The scary thing, though, is we don't know A, how much it's actually soaking up, or B, how much it can actually hold. And so both of those are scary because one of these days the ocean's just simply going to be full, and then we're really in trouble, but we don't know when that is. All right, moving to 120. Okay, carbon shifting. That's basically what I was talking about here. Okay, Earth's crust, or I was talking about earlier, Earth's crust, the lithosphere. Okay, moving stuff to the atmosphere. So, for example, get this diagram here. Okay, so sedimentary rock, there's the fossil fuels I was talking about right there. Fossil fuel extraction, anthropogenic sources. Anthropogenic means human, is what that means right there. Okay, it goes to human sources, fossil fuel combustion, up to the atmosphere. That's my sweet example that I was talking about earlier. It's carbon shifting is what's going on there. All right. So right here at the bottom of 120, I write climate change questions, carbon sink question mark. That's what it's talking about here. Science remain baffled about the so-called missing carbon sink. Of the carbon dioxide we emit by fossil fuel combustion and deforestation, researchers have measured how much goes into the atmosphere and the oceans, but there remains roughly 2.3 to 2.6 billion metric tons unaccounted for. That's scary. Okay, like it says, there are many scientists think they're taken up by plants and soils, but they're not sure. And that's kind of the nerve-wracking part with the carbon cycle. All right, now this, page 121, this is the nitrogen cycle. Okay, it's very, very, very important for all the living organisms. And this is why you guys are planting the little legumes, because that's going to make the nitrogen accessible to the other plants that you've planted in your eco columns. All right, biologically active nitrogen is typically the limiting factor for plant growth. That's why fertilizer is nitrogen based. So if your grass isn't growing or your crops aren't growing, it's most likely because there's not enough nitrogen in the soil. So farmers and your parents and whoever put fertilizer, which has a lot of nitrogen, on the grass to make it grow. Because like I said, it's the limiting factor. Okay, so nitrogen cycle here. So you can see extraction and combustion from fossil fuels. You got nitrification, fixation by lightning. Denitrification basically is going from here to there. Okay, so you got nitrification goes one way. You can see right there, nitrification right there. Denitrification comes up. All right, I'm confident you guys did this in biology. So if you need to spend some more time looking at it, this is page 121 again, to kind of walk through this stuff. Okay. Nitrogen fixation. Now we're at page 124. I'll dive into it a little bit more detail here. Okay, so again, page 124 right there. Nitrogen fixation has basically two big steps here. Okay, so you can see step one, and I've written it out. Bacteria or lightning perform. So basically, we're taking N2 from the atmosphere, N2 gas from the atmosphere. The bacteria or lightning change it. Bacteria can do it. They put some energy into it. Lightning perform it. Lightning simply has energy involved in it. So you snap some lightning in the atmosphere that hits the ground. It'll grab nitrogen and automatically change it into ammonia. Like the lightning energy source is what causes this to happen. Okay. Second step, it goes from ammonia to ammonium. Okay. This is nitrogen fixation. Okay. Now the nitrification process here takes that ammonium, shifts some stuff around, turns it into nitrite. Then shift around a little bit more, makes it nitrate. Fertilizers give plants the nitrogen they need, because this right here, that nitrate, that is what the plants need. That right there. We have that in the atmosphere. We need to get to that. So the bacteria have to do it, or the legumes. One of the things you can see here, I'll put up on the screen a little bit, those nodules right there, that is where the bacteria live that do nitrogen fixation. So the plant is basically giving them a home, because this is mutualism relationship. They live on the nodules, so that way the bacteria can take the nitrogen from the atmosphere, turn it into nitrate, and that way the plant can use it. Okay, this bacteria is what's called nitrogen fixing bacteria, as you can see right there. Okay, because as the name implies, they fix the bacteria. All right, moving to 125. Okay, there's very little phosphorus in the air. That's the big thing you need to remember about this, about the phosphorus cycle. Okay, I'm going to take this off so we can point to it. So you can see a lot of it is in rock. Okay, geologic uplift in the rock. There's weathering, which goes down to the rivers, into the water, buried, back into the rock. Okay, again, it's very, very, very little in the atmosphere, because phosphorus quickly gets grabbed up by anything and everything. So if it's in the air, it's going to be grabbed by something really, really, really quick. Okay, now we're flipping to 15.1. 15.1 is on 385, talking about freshwater systems. Okay, I don't have a sticky note here, but basically I want to kind of walk through this. So you can see all the water on our planet. You can see oceans are 97.5% of that. Okay, freshwater, 2.5%. That's all that it is. Out of that 2.5%, 79% of it is locked up in ice caps and glaciers. Okay, and obviously we know that both of those are starting to melt, but that is flowing into the ocean, typically not like flowing into our rivers. So we're losing that freshwater source. So of the remaining, we got 20% in the groundwater, and then we got surface freshwater is only 1%. So 1% of the 2.5% of freshwater is on the surface. Break that down even more. You can see lakes, soil moisture, atmospheric water vapor, so on and so on. Like comparatively, there's not much that we can get to. And that's one of the scary things about, like, watering your lawns and things like that. That's why in California they limit how much water you can put on your lawn, as you go straight up, run out. All right, where are we at now? 388. Talking about surface water versus groundwater. Name implies it's above ground or below ground. Surface, on the surface, below the ground. Pretty straightforward. Okay, groundwater is contained in what are called aquifers. You got to know what that term is. okay, which is like a giant sponge. It's basically a big area like this that basically the water can kind of soak into. It's rocks, but the rocks are porous. Okay, so the rocks can soak that water up. All right. So I'll put a picture right here real quick before we get to that sticky note from 389. So there's the lake right there. Okay, look at the rock there. You can see that it's porous. You can see there's a well there tapping into this one. Okay, a bigger well goes to the deeper one. Okay, confined versus unconfined. What that means, basically unconfined, you can see that there's a lake sitting on top of it. Okay, that's what means unconfined. So basically it's exposed, quote unquote, to the surface. Whereas a confined aquifer, it doesn't have like a lake that kind of can fuel it. The way it gets recharged, if you follow it over there, it's just kind of like at the foothills. It just kind of soaks into the ground and recharges it. Okay, so this is what an aquifer is. So a lot of wells will tap into stuff like that to get their water. But if you're pulling more water out of these aquifers than is going in, then you're going to dry the things up. You're going to have to drill farther and farther and farther and farther and farther down. All right, let's talk about the sticky note real quick. Recharge zone is where aquifers get water added to them. Like we're showing the picture, the lake does it, or the kind of the foothills can do it there. Confined versus unconfined, we talked about that as well. Contained between impermeable layers, that's confined, and it's harder to get to. And I'll swing back to that picture in a quick second. Unconfined, not contained by an upper layer, and it's easier to get to. Again, it's closer to the surface, farther away from the surface. The impermeable layers, we'll talk about that real quick. Put that picture back up there. Okay, you can see the layer is right there. Okay, you see upper confining layer and lower confining layer. Clay does not allow water to get through it because clay doesn't have any pores. All right, this picture here, I want to kind of take a little bit of a side note here. Okay, you can see basically where we're kind of zoomed into the Midwest. Okay, there's Nebraska, Colorado, Kansas, a thing called the Ogallala Aquifer. Okay, Keystone Pipeline, the pipeline from Canada goes like this currently and then drops straight south. Keystone Pipeline would have cut across it to basically like save time, kind of like, you know, hypotenuse for a triangle, would have cut straight across. The big pushback, and the reason it eventually got canceled, if there's a big pipeline right there and that pipeline breaks, it will soak into that aquifer. That aquifer gives water to basically all of our plant or all of our farmland that way. So if our farmland aquifer gets, you know, like infiltrated by the oil, like the whole production of food that goes down in that area big time. All right, so oligotrophic versus eutrophic lakes. We talked about this already real quick. Low in nutrients but high in oxygen. Think of this as like the mountain lakes, really clear and beautiful. There's not many nutrients, so that's why there's not many things there, and that's why it's so clear. Eutrophic lakes, high nutrients, but low in oxygen. There's a lot of pond scum there, because if there's high nutrients, there's a lot of algae that live on the surface. That algae dies, decomposition eats up oxygen. All right, so basically you want something in the middle. You don't want something that doesn't have any nutrients, but you also don't want too many nutrients. All right, page 392. The wetlands. Okay, the soil is saturated with water. There's very, very, very high biodiversity. Provides important ecosystem services. Okay, water filtration is a huge one for wetlands. So the water from the rivers that has pollutants in it dumps into the wetlands. The ecosystem services cleans that water before it gets to the ocean. Water supply and demand problems. There are lots of dams that are made. Okay. Here in Washington, we have tons of hydroelectric dams. A third of the major rivers are experiencing reduced flow from climate change. So all the electricity that we're getting from those hydroelectric dams, the reduced flow, we're not generating as much electricity. And so that's where the need to kind of diversify electric energy production begins. Page 393, consumptive use of water. So basically you're removing water from an aquifer and you not return it. So again, you're pulling more than you can be put back in. Irrigation of farms is a major one. Okay, California, the farmers are having to drill wells to 600, 700, 800 feet to try and get to the different aquifer. Then there's a thing called non-consumptive use. It does not remove or only temporarily removes the water. Okay, hydroelectric dam is basically an example of that. Okay, you're kind of removing the water, quote unquote, from the river so it can spin a turbine. Then you're putting it right back in. Okay, so you're kind of temporarily removing it, or you can think of you're just straight up not removing it at all. Either one, that's going to kind of define what a hydroelectric dam does. All right, we're on where we at? 395. I don't have that written down there. 395. Unsustainable water mining is causing lots of problems. So lakes and rivers are drying up. I'm confident you guys have seen pictures of Lake Mead these days. All right, aquifers are being used faster than they can be replenished. Again, consumptive use. You're pulling more than you're putting back in. And the water tables are dropping. All right. Salt water can also infiltrate the aquifers. So, like if you're close to, I'm going to move it a little bit. If you're close to the coast, like in California here, if you get that thing so dry, the salt water will start to move into your aquifer, and then that aquifer is basically no good anymore. Because you obviously can't, water your farm with salt water. That's not going to work at all. 396. I didn't write anything there. 396. So aquifer and groundwater depletion is causing the ground to sink as well. Because basically, think about it. If you have something under the ground that is non-compressive, or basically you can't kind of squish, that's water. And also when you take it away, that ground is no longer as stable as it used to be. Mexico City, the whole thing is down 33 feet because of that, the whole city. The California agriculture regions, down 30 feet. The buildings start to lean, the pipes break, the sinkhole happens, so on and so on. Okay? Say no to bottled water. That's basically what I talk about here, which if you read the paragraph right below it here, that basically talks about what's going on. Okay? In general, just fill up a hydro flask. That's all you should do. The water that comes from your tap water has more nutrients and minerals than the bottled water typically anyway. All right, flooding. It's a good thing. Okay, a lot of people hate it, but it's actually really, really, really good thing. That's why the Amazon rainforest has such high biodiversity, is because it floods so often. You can see it spreads nutrients over vast areas, creating rich topsoil. We don't like flooding though, because again, ruins houses and property. The levees are built to control the water levels. So a levee would basically be this thing right here. Okay, it's basically a big cement kind of channel that controls where the water can go. Because again, we just have too many houses and too many things that are built kind of right in the floodplains. So, hey, I don't want my house to sink. So the city or the county or the state, whatever it is, you guys need to control the flooding so it doesn't wipe me out. Side note, is your bottled water as safe as you think it is? Read that. Pretty interesting. All right. Some dams are being removed. Yeah, well, I think we're done for there. All right. So you guys know what to do. Leave some questions so we can chat.